next up we have Devin, who's going to talk about Fourier transforms. So, warm round of applause, please.
When I was studying for my undergraduate in physics, I learned about this thing called the Fourier transform. First looking at it, it looks like a slightly horrible bit of maths. It's very useful in solving lots of physical problems, but the most wonderful thing about this is that actually it's something that's happening in our brains every second. Now, we can now look at the ear. We know that sound is vibrations in the air, and these vibrations come and beat against the eardrum. Hear a cat. Or a lion. One of these is very safe, the other one means we should start panicking and run away. But looking at these two vibrations in the air, they don't look that different, and there's no way we can look at one and say that's definitely a cat and that's definitely a lion. So we have to understand more about how the brain interprets this sound. So sound beats against the eardrum, and that passes the vibration into the spiral-shaped bone called the cochlea. If we look closer inside the cochlea, we see that there's these billions of tiny little hairs. Each hair has a different length, and because they're different lengths, they have a different resonant frequency. This is very similar to a guitar, where each string has a different resonant frequency, and that resonant frequency means that it will have a specific sound. So if I touch tuning fork onto a guitar, it makes one piece of paper vibrate a little bit, not very easy to be seen, and the other one makes the other one move. And that's because these two strings are in resonance with the sound made by the tuning forks, and that's what's happening inside the cochlea. So, for any sound that comes in, each different frequency will make a different string hair vibrate, and that builds up this thing called the Fourier transform. So, if we look again what's going on, but this time out in the brain, sound comes, and the brain produces this Fourier transform, which shows how much of each frequency is in the sound, and it's almost like a fingerprint for that certain sound. So, the brain looks at the Fourier transform that's made, and it says, ah, that's a cat. So a different sound comes in. It produces a completely different Fourier transform, and by seeing what frequencies are in there, it can say, ah, that's a line, and now it's time to run. So this is something that it blew my mind to think that this complex mathematical thing is something that our brain does all the time without us even realizing it. And now that we've discovered it and we can model it with mathematics, we can use it in physics. It's very helpful for solving problems, but we also use it in technology. And things like the push-button telephone, a Fourier transform is done to work out if you're pressing a 1, 3, or a 9. Fourier transforms can even be used if, instead of using frequencies, you have very basic faces, and by doing a Fourier transform of somebody's face, you can get this characteristic fingerprint, and it's used in face recognition technology. So it is a really wonderful thing that has so many applications in physics and technology. But if you would like to try a Fourier transform at home, I will leave you with this final warning.
We're going to talk about strobing, or has strobing in it, but due to the health effects, we were actually banned. There's got to be a lot of that in here that we had problems with health and safety, but hence the talk, because I don't know if any of you have heard about it, but photoepilepsy, or photoepileptic seizures, that people sometimes call photosensitive. Now, this actually occurs due to repetitive flashing lights or sounds. Now, this little character here is called Pikachu. He's a Pokemon, and he's kind of a cross between a cat and an electric eel. And when he gets upset, angry, or annoyed with people, he seems to discharge electricity. Now, the reason he's up there is because this guy here is responsible for the largest amount in one go of photoepileptic seizures. Okay, now you would believe believe that, would you? But in Japan, in the 1990s, and probably still so, Pokemon was the biggest thing going. And in 1996, on the 16th of December at 6:30, an episode called Porygon, Digital Warrior, was shown. At the time, 50% of all children in Japan between the ages of 5 and 16 were watching this show. Now, 6:51, for some unknown reason, it's probably clearer in the cartoon, Pikachu set off some sort of lightning attack. Now, I've slowed this down for reasons you're about to find out. At the same time, 12,000 children had photoepileptic seizures, ranging from vomiting, diarrhea and headaches, all the way up to full-blown fits. Okay, 900 children were hospitalised. Now, if you think that's funny, it gets better. It's such a massive story in Japan. They had to talk about the news. 12,000 children injured by a TV program, 900 sent to hospital. So they talked about the news. Unfortunately, they kind of forgot what triggered. So at 9 o'clock, leading news, that clip was shown again. Now, not only a whole raft of children were sent into photoepileptic seizures, but their parents were as well. So it's a great way of bringing families together. Don't do things as families. Clearly, the kids had photoepileptic seizures. So anyway, there was going to be a talk on that, but I'm quite glad there wasn't because it could have got a bit messy. But anyway, I'd like to introduce our next speaker, Emilio, all the way from Mexico. Almost. And he's going to be talking about weight. So, big round of applause for Emilio, please.
Hi. Today I want to talk to you about something I'm sure you've all seen and perhaps wondered about, but maybe you haven't really thought explicitly to the question, why is this happening? It's the weight behind the boat. It's this triangular shape that you see, and it's funny because it's always the same sort of distinctive pattern. It's two big waves with smaller wavelets across at an angle, and if you're lucky, you get these sort of stripes as well. And if you look at it closely, you can see that it doesn't depend on almost anything. It doesn't depend on the size of the ship. It doesn't depend on the speed it's going. It doesn't depend on its shape. In fact, it doesn't even have to be a ship. It can be something as small as a dock. This is actually a photo I took at the Round Pond a couple of weeks ago. And it can also be seen at the very largest scales you can conceivably think of it. This is a picture of the Sandwich Islands. They are 400 kilometers apart, more or less. And this is actually the atmosphere flowing over them and making pressure waves with the ocean and the lowest layers of the atmosphere, making this same pattern on the clouds above the ocean. And it's exactly the same pattern that you see behind the ship. So the question as a physicist is, what is the fundamental bit of physics that underlies all of these phenomena across all of these different ranges of scales? And the answer is that wherever a ship is, it sends out ripples. And they're the same ripples you see thrown up by a stone. But of course, a ship is always there, so it's always sending out more ripples. And wherever it is, it's sending out ripples and more ripples. And as Joe told you, waves can add up or subtract, so they will interfere and they will create a pattern as a whole. So the whole of the ship's trajectory will act as a source, and it will all come together to make this beautiful wave pattern. And it's almost like the ship is trying to outrun the ripples it's doing. But then, as a physicist, one questions, if it's outrunning the ripples, why does the shape not depend on the speed of the ship? Surely it will get shallower the faster you're going. And if you take more ships and set them all going at different speeds, so this is going about 3 times faster than this guy, you can see that they're all making the same pattern overall, but the size is different. And what this tells you about the waves is that faster waves are larger. So waves that have a longer wavelength will travel at a faster speed, and the faster the ship is going, that will just make a larger pattern. And this you can see, in fact, just by chucking the sun into a pond, and you'll see the longer wavelengths coming out first, and after that, the smaller ones coming out. And in fact, the smaller wavelengths were already there. They were stacked on top of each other, giving detail to the initial perturbation. But as time goes on, and the longer wave, and the behind the physics behind the wakes, because all of the power given out by the ship's engines all the way back there is, well, most of it going into making the wake. And in fact, there's so much power that you can be miles away. Oh, sorry. You can be miles away from the ship, and the wake will still be high enough for you to surf in. So that's why this was this goal in front of ships, to make another wake pattern that is a little bit ahead to try and cancel out the one made by the ship. And it's really important to do that because in fact they can be so big that they can even sink ships if the original ship is going fast enough. So those are a couple things to think about when you see a nice wake pattern like this one.
Hopefully he's kept you all wide awake.